Okay, starting this lecture is Thank You Prometheus. The quote we have is Prometheus, thief of light, giver of light, bounded by the gods, must have been a book. And so this whole lecture is going to be about light. Learning goals that we have for this lecture. Students will be able to differentiate between the ground state of an atom and the excited state of an atom. And those are good vocab terms right there. We need to know what both of those are. Number two is to relate the quantized energy of light to the Bohr model of the atom. And so we've talked about the Bohr model of the atom in our Unit 3, and we're continuing it here. And then lastly, understand spectroscopy as an experimental tool. So jumping into this, what we already know, or what we should already know. Atoms consist of protons, neutrons, and electrons. And electrons must be at a definite or defined energy level, and we call these 1, 2, 3, and 4. And this is what we learned in Unit 3 when we talked about the Bohr model of the atom. What we learned in the lab when we put the different colors of the different transition metals in the fire, we saw that we had different colors of light. So different elements burn with different colors when exposed to the same flame. And so we can see just a regular flame here, and then moving on we see different colors of light, and the colors are consistent with the uniqueness for each atom, and so as each atom will have its own individual color, and that we're going to learn because of those energy levels. Electrons. Now, electrons, what we've talked about so far, they're just negatively charged particles that they orbit they kind of move around the nucleus, and we've said that they're at distinct energy levels. But electrons can exist in a numerous amount of energy levels. The state of an atom is determined by the energy levels of an electron. And so we can have electrons in our first energy level, our second, third, fourth, and so on. And they can exist in all of these. And so a ground state electron, the electrons are in the lowest possible, and this is the big thing here, lowest possible energy level. And so the electrons are existing, and not all of them can actually fit around that center atom, that first energy level, but they get as close as they possibly can. And atoms always seek to be in the lowest energy state. They never want to be in an excited state. They want to exist in that lower energy state. And the lowest energy state is the closest it can be to the nucleus, and the closest it can be to the nucleus. Because once we fill up this first energy level, what we'll see is that the electrons have to go in the second energy level. And once that fills up, then they got to go in the third, and so on. But basically what they'll do is they'll go to the lowest energy that can actually hold them, where they can actually fit. The excited state, that is when electrons are at higher energy level than the ground state. So it's just the excited state is anything above the ground state. So anything where an electron is jumped. And you can kind of see the picture here where the electron is sitting on that first energy level. It's right there. And then in the excited state, we see that it's jumped. It's gone to a higher energy level. Now, atoms need to absorb energy to reach this excited state. So we still have to follow the law of conservation of energy. So if this electron moved from that inner energy level to a higher energy level, that had to absorb some type of energy, because it just can't move on its own, so it has to absorb energy. Now the excited state is signified with an asterisk, so you can kind of see it down here, and so we would say that we're saying that this is a hydrogen atom, and so that electron is jumped, so it's in an excited state, so we put that asterisk, and the asterisk is what's right there. That's the asterisk. And we signify it by just saying, hey, it's in an excited state. So there's at least one electron that's in a higher energy level than what it should be. Now, electron excitation. Energy is always conserved, which we just said, the law of conservation of energy. And so it's always conserved, and electrons move up in energy levels when atoms absorb that energy. Now, we've been used to some types of energy, even if we didn't know it or not. Some common forms of energy absorption, the electromagnetic spectrum, so light, it can absorb light, collisions, so it can actually collide with something, or heat, which we saw heat we used in the lab. When we put it in the fire, it absorbed that heat. So any type of absorbing any type of these radiations, or the radiation or the collision or the heat, will cause it to get excited and jump energy levels. Now, electromagnetic radiation. So this right here, we talked about electromagnetic radiation, that spectrum. It's radiation produced as an electron moves from an excited to a ground state. And so when we actually have this, what the color that we are actually seeing in the lab from that electromagnetic radiation, it's when the electron drops back down. Electromagnetic radiation can only have the same energy as the difference between the energy levels. So it's a very specific energy. So we had an electron that jumped up here to a higher energy level, and when it drops back down, it emits that light. It follows the law of conservation of energy. If it absorbs some type of energy, when it falls back down, it will emit a same type of energy that it absorbed. And so we see this, and the key thing here is that when it moves from the excited state to the ground state. So say we go from energy level 3 to energy level 4 to energy level 3, we will have an emission of light. So we'll see a color of light. But on the other hand, if we go from energy level 3 and we go up to energy level 4, you don't see an emission of light. It just absorbs that energy. So it's only when it drops down, when it goes down in energy level, that you see that light. So let's look at an example. So in looking at this one, we see our proficient question, proficient A1, and it says, draw the atomic model for the following states of helium. So here, since it doesn't have an asterisk, we're going to draw the ground state. So all we would do for this is we have our helium, which will have 2 protons in the middle, and then we have our first energy level, and we have 2 electrons, and we'll draw those different colors. So here's our electrons, 1 and 2. And then we'll say that there's another energy level right there, but right now they're in the ground state. They're in the lowest state possible. So we'll draw one here. Since we have the asterisk, we'll draw it in the excited state. There's our 2 protons. Here's our first energy level. We'll say there's 1 electron there. And then in the second energy level, we'll say that since it's excited, we'll put an electron in the second energy level. And so it jumped an energy level. This would be our excited state because it doesn't look like the ground state. It's in a higher energy level. Moving on to our next one. It's our mastery level question. Burning hydrogen in a flame produces a series of colors shown below. And so what we wanted to do is design an experimental method to produce only this red light. An answer to this would be that electrons transition occurs only at specific energy levels. And so by controlling the temperature of the flame to a very low temperature, you could permit only that specific transition. So what we could do is we could control the energy that went into it. And what we're saying here is that, remember, it takes a specific amount of energy to jump that energy level. So if we keep the energy really low, then it'll jump a very low energy level and we'll get this color of light. Now, energy of radiation equation. So the energy of radiation, we can calculate it using this equation. E is our energy. It is measured in joules, and it's just the measure of an object's ability to interact. This H value is Planck's constant. It is kilograms per meters per second squared, and so we can say it's the basically the value at which all energy values must be a multiple of, and so it's just a constant. You can find this on your formula chart. It is actually 6.626 times 10 to the negative 34th. That's actually the number. And then F is our frequency. The unit is hertz, and the definition of it is the number of waves per second. So let's jump into a question using this. So it says, label each of the variables and rearrange the following equation to solve for the frequency. So we know that this is energy, we know that H is Planck's constant, and we know that F would be our frequency. And so what we want to do is algebraically rearrange it to solve for frequency. So all we'd have to do is just divide both sides by H, and we get, those guys cancel, and we get frequency equals energy divided by Planck's constant. And we've solved for frequency in that equation. Jumping to the next one, Proficient B-2, it says, what is the total energy in a yellow photons? So we're looking at what's the energy of yellow photons. If the wavelength of yellow photons is 5.17 times 10 to the 14th, and we're going to say that that is our frequency. So if the wavelength of yellow photons is 5.17 times 10 to the 14th hertz, and that hertz right there, that is our unit for frequency. So when we're using this, we're going to use the equation E equals HF. Okay, and here, since we have our frequency, we're solving for energy. And all we have to do here is plug it in. So energy is going to equal Planck's constant, which is 6.626 times 10 to the negative 34th. And all of that multiplied by our frequency, which is 5.17 times 10 to the 14th. And on here, make sure that we're plugging it into our calculator correctly. And we should get an answer of 3.43 times 10 to the negative 19th joules. And joules is our unit of energy. Our next one, it says, what is the frequency of a red photon, which has an energy of 2.65 times 10 to the 19th joules? And so what we're doing is we're solving for frequency. So we have energy equals Planck's constant times our frequency, and we're solving for our frequency, so we divide both sides by h, and frequency equals energy all divided by Planck's constant. So we set this up. Our energy is 2.65 times 10 to the negative 19th, all divided by Planck's constant, which is 6.626 times 10 to the negative 34th. We go ahead, plug this in our calculator correctly, and we should get an answer right around 3.99 times 10 to the 14th hertz, because hertz is our unit for frequency. On to the next one. It says how many red photons, and it gives us the frequency here, would it take to equal the energy of 4.62 times 10 to the negative 18th joules? And so what we are trying to do is we're trying to find out, the equation that we've been using is just for a single photon. And so we want to know how many photons it would take to equal that amount of energy. So what we can do is let's find the energy of one photon, and then what we can do is just divide it. So energy equals Planck's constant times our frequency. So we take this and we take our Planck's constant, which is 6.626 times 10 to the negative 34th, times our frequency, which is 4.0 times 10 to the 14th hertz. We go ahead and calculate this, and this will give us the energy of one photon. So 2.65 times 10 to the negative 19th joules. That's the energy of one photon. So what we want to do is divide this energy by the energy of one photon, and we'll see how many photons we actually need. And when we do that, divide this number by that number, what we get is we get an answer of right around 17.43 photons of red photons, which we would actually need to get that energy. Moving on to spectroscopy. Now what spectroscopy is a division of chemistry and physics, and it's a study of the interaction between light and matter. Measurements are made with the spectrometers or spectrophotometers, and so you can kind of see a picture here how we're breaking up the wavelengths of light, and we're studying those. And what we looked at when we're actually looking in the lab when we're burning those things, what we would look at is we would look at an emission spectroscopy. And what happens when they actually do this the sample is energized, and so what they're doing is they're energizing it. They're putting energy into the sample, just like what we did. We put energy into the sample by heating it up. You could also put energy into the sample by exposing it to light, but we just heated it up in the lab. The atoms goes back and forth between the excited and the ground state. And remember, when it goes from excited to the ground state, light is produced. And the light produced is measured. And we measure it basically by taking it through a grating, and we break it up into the different colors of the light. And what we can do is we can measure it and we can quantify everything. And what we can do is, by doing this, unknown samples can be determined by comparing it to known spectra. So if we don't know this, and they do this a lot with stars, what they'll do is they'll take stars and they'll take the light that comes from stars and they'll analyze it to see what that star is made of. And so we can see if we have a emission spectrum that looks like that, we know that it's lithium. Lithium will have that emission spectrum. And all of this comes back to basically the pull between the protons and the electrons in the atom. The more protons we have, the more pull we have, and what happens is we have very specific bright line. We call these bright line spectrums. And so every single element has its unique spectrum. And we can kind of think of these guys as a fingerprint. Every element has their own fingerprint. They have their own bright line spectrum. So let's look at an example with this, and it says which element is present in the unknown sample. So we could pretend like this is an unknown sample that we got from a distant star. And what we want to do is we want to see what elements make up that star. And so what we can do is we start comparing our wavelengths. So we can see that here in carbon we have 477 nanometers, and in our unknown sample we have a line here at 477 nanometers. We see we have a 393. We also have a 393 in our unknown. We have a 538. We also have a 538. We have a 600 nanometer. We have a 600 nanometer. We have a 658. And we also have a 658. And then we have a 712. And we look in our sample, we also have a 712. So by comparing our unknown to carbon, we know that this sample of light will have carbon in it because it has all the specific wavelengths of light at the right time. Now, if we're looking at our other one that we have here, and this is iron, and so we're looking at iron spectrum, we see that we have a 392, and we look up here, we don't have a 392. And so since their spectrums don't match up, we don't have iron in that sample. So what we would say is that we have carbon in there and we have something else, and we'd have to compare it to other ones to figure out what it was.